Good afternoon, everybody, and thank you very much for being here today. My name is Anna Waman, and I want to start off by apologizing for not being able to be physically here today. I would also like to give my deep thanks to the session chairs for helping me in delivering this talk using this video. Alright, about this talk, the title of this presentation is Combining Arm and Hand Metrics for Sensible Grasp Selection. This work has been done at Georgia Tech in collaboration with Professor Henny Benamor from Arizona State University and Professor Henrik Christensen, currently at UC San Diego. Alright, let's start with the motivation for this work, and it is obviously manipulation tasks. I think that manipulation tasks are pretty important in comparison with other human activities, because they allow humans to interact and modify their environments to suit their needs. Now, if I would go around the audience and ask each of you to name an example manipulation task, I would get a very long list. And probably we would have a lot of example manipulation tasks with very different degrees of complexity. While it's true that in our everyday life we use manipulation tasks that are really complex, it's also true that there are a lot of simple manipulation tasks that in fact are so simple that they can be performed by humans that are not that experienced in manipulation, such as kids. So here are 3 examples of simple manipulation tasks that I particularly like. Picking up objects, pick and place, moving an object from a start location to a final location, and pouring, changing the contents from one object to the other. In this talk, I'm only going to talk about the pickup task, and at the end I'm going to mention some thoughts about the other 2 tasks. Alright, pick up objects. Even a kid can do it. Of course, the question that I have is, can a robot do the same? Can the robot be able to pick up an object in the same manner as a kid can? Well, there are challenges for this, and perhaps the most important that I can think of is that although the tasks seem really simple, in fact, even for something so simple as picking up, the robot has to make a decision. From a set of virtually infinite grasps, which grasp should the robot choose to plan a motion? So, well, here again the question, how to select a grasp from a set of many possible grasps. You could either select a grasp randomly and then try to see what happens, but that's not a really smart idea. Usually what people in our community does is they use a metric to evaluate a set of candidate grasps, and then they select the grasp that has the best metric, and then they attempt to plan an arm motion. Now, of course, we need a metric for this. In literature, there are a lot of metrics. A recent review counted 24 metrics. Now, the most common metrics are the analytic metrics, and one of the most popular is the epsilon metric. And well, here we have a representation of this metric and a derivation of this one. The main problem with using these analytic metrics, as probably most of you know, is that they assume a set of ideal conditions, such as Coulomb friction, not interaction between the hand and the object, point contacts, and so on. And in reality, this is not how a manipulation task happens. There are different factors that affect using this manipulation metric. Now, there's another reason why this metric is not really good, and here is an example. Here we're seeing 3 pickup tasks, and as you can see, the grasp comes towards the end of the task. Before even doing that, the grasp, the robot has to reach the object. So When we talk about manipulation, we have seen a lot of interest in the grasping part, but what sometimes we might forget is that before grasping, you need an arm motion. In the pickup case, you need to reach. And let me illustrate the point a bit more in this example. You have here an object that a Pringles container that you want to pick up, and here you have three grasps, three possible grasps, and three of them work. With three of them, you pick up the container, and it is on the hand, so the hand is holding the object. Now, if I ask you which grasp you would prefer, probably you would agree with the happy faces that you see there. Probably you would prefer the grasp here because this configuration of the arm looks better. You may want this one that has the elbow up, that may not be very comfortable for the robot if you wish, and you definitely wouldn't like this one because this looks awkward and the arm is very close to the robot body, which may produce collisions if the movement is not precise. So again, I really want to reinforce this point in the talk. A manipulation task is not just about grasping. What I think is that we should be really interested in considering the reaching part of the task. Ideally, when we select a grasp to perform a task, we should select a grasp that entails simple reaching movements, grasps that allow the robot to perform movements that are easy to plan, and in turn this means that they would need only short execution times. And this is more importantly, and this is something probably most of you observed when operating a real robot. If the movement for the robot is simple, there is less accumulated actuation error. But if the movement is complicated, like the movement in the grasp 25, it's pretty likely that error is going to accumulate, and at the end when you want to execute the grasp, probably you're going to have more errors, which may cause the grasp to fail. So, question again, how to select a grasp? We agree that we need a metric, and we have seen that most of the classical metrics only focus on the grasp aspect, on the contact points, on the relationship between the hand and the object. I have tried to make the point that for a manipulation task, it would be a good idea to take into account the arm motion. Hence came the idea of using two metrics, the arm metric and the grasp metrics, and combine them in some manner to generate a manipulation metric. Here I'm abusing of the word metric for manipulation. Probably would be better to say a manipulation measure, a way in which you can rank grasps to see which one you select. By now we'll just use metric to make it easy to explain. So let's start with the R metric. Which R metric do we plan to use? First off, when you have a metric, you have to think what you care for, what you want to measure. For simple pick up tasks, the metric is really simple. What you want when you move an arm is to avoid collisions with the environment and to get easy movements. Now, usually, again, this is something pretty intuitive, but I think it's good to say it. Plans are easier to execute if the arm has a lot of possible configurations, has a lot of possible options to accomplish the final motion. So the arm metric that we use in this work is simply for redundant arms, just a number of discretized IK solutions that allow the arm to execute a given grasp. For the case of our robot, this has a 313 configuration, so the IK is a semi-analytic solution. So it's pretty easy to discretize the possible IKs. Now, in some previous study that we had, we suggested that instead of using just the number of IK solutions, we could use the average of the manipulability of these IK solutions. However, we found that using just a number of IK solutions, which is a very simple calculation to do, give us the best results, as we will see in a bit. Alright, so we talk about the R metric, and now I want to talk about the GRASS metric. Again, we ask ourselves, why do we need this metric? What do we want to measure? When we use a GRASS metric, what we want to the grasps we want to favor are grasps that are stable. So technically here we could use any grasp metric available, like epsilon, the one that I mentioned, or any other. However, for easiness to calculation and for our particular hardware, we chose a very simple metric, which is the distance between the hand approach direction and the centroid of the object. And just to give an intuition in this image, you can see that for these three grasps, probably if I ask you which one you would choose to execute, you would choose to select the second grasp, mainly because it's holding the object near its center of mass, and intuitively you would think that they would guarantee more stability when grasping it. Alright, well, this is just an algorithmic version of the R metric and the GRASS metric I mentioned. This is on the paper. And now it's time to combine these two metrics. Now, to get the manipulation metric that takes into account both of these. As I mentioned, the GRASS metric has length units, the distance between the approach direction and the centroid, whereas the R metric is non-dimensional. It's just a number of IK solutions. So how do we combine them? We could talk about this at some other time, but we tried a number of possible combinations, including weighted additions, or we tried many different ways. The way that we found to be most effective in terms of success of execution was to use a two-step approach, and I'm going to explain it here. Imagine you have a set of candidate grasps. The first thing you do is you use the R metric, the number of IK solutions for each grasp, to partition this candidate grasp set in 4 sets according to the R metric. The sets have very good metric, good, fair, and bad. Now, once you divide this, once you have these sets, the next step is now to use the GRASS metric to order the grasp within each subset. So you use the GRASS metric, and now you have these subsets organized. And finally, you just put them together. And now, instead of having just a number of candidate grasps, now you have an ordered set of grasps, in which probably the grasp that you would like to try first, the grasp that you would like to attempt to use, is the grasp that is on top, and the grasp on the bottom you would try to avoid or to use it as a last option. Again, here that this is just the algorithmic version, and now what I guess would be of interest to you. How do we evaluate this ordering of the grasps? We did experiments both in simulation and on the real robot. We used 9 object models from our dataset. Those objects are just household objects, and the models here were obtained using a superquadric approximation using the one viewpoint clouds that we get from the robot. What we did is, for a simulation part, we just generate a number of random poses for an object on a table, and we use our combined arm and grasp metric to select the grasp to use, to select the best and the worst grasp, and we compare their performance. Here are some examples on a simulation of the grasps considered the best and the worst for 3 different objects. The upper row are the best grasps and the lower row are the worst. Again, this may be obvious, but I think it's good to mention. If you notice in the first row, The best grasp tend to be grasps that have the arm in first a position that has a lot of freedom of movement, like a lot of possible ways in which the robot can execute this grasp. And if you see, the grasping tends to have the object around the center. In the cases that are deemed the worst, you can see that first the arms are kind of dangerously close to the robot, and it doesn't actually hold it from the center. Well, there are some exceptions, but that's in general. So what we found, here are the 9 objects we use, is that in general the success rate for using the grasp with the best metric was generally higher than in the worst case. And in planning times, and this is interesting, that the planning times for the best using the grasp deemed the best by our metric were usually at least half the time than the times used for the grasp that is considered the worst. Alright, I may be running a bit out of time, so we also did this on our actual robot. We again used the 9 objects that we mentioned before, and we put the objects in 10 different locations in front of the robot. I should mention that again, we don't have the models of the objects. These models are generated online, so sometimes there are errors in the modeling that may influence the grasp failure. We still consider this in our final results because that's just part of using a real robot. For instance, in this example, you can see 9 grasps of one of the objects, the plushie, and it fails twice. In general, we execute 98 grasps. We had 88% of success, and failure were 12%. And we noticed that most of these failures were due to either modeling errors or sleeping. Most of them really were actually looking pretty close to actually work. And here we have just some videos of some of the 9 objects in different locations and the robot selecting autonomously which grasp to perform. Now, the summary of my talk today is, again, the most important thing. You may want or not use my arm and grasp metric, but what I think is important from today is that when you choose a grasp, you should not only think about the hand-centric aspect. You should also think of what happens before you grasp an object and how the grasp selection influences that reach in motion. If you select a grasp, at least considering the arm aspect, we have shown that in general you get shorter paths and with faster planning times. Now, a caveat that probably some of you may be thinking is, okay, she's just dealing with pickup tasks. And that's just a very simple task, right, with only one step. What happens when a task has more steps, such as pick and place and pouring, the task that I mentioned at the beginning? Well, I couldn't talk about them in this paper for lack of time. So this is just a sneak peek of, let me lower the volume. We apply this metric with a slight variation, not really that much, for pick and place tasks with different constraints and with pouring tasks. And well, that's right now under submission, so I cannot give too much details, but you can see that this metric is still used and it gave us actually really good results with very minimum changes. Alright, that's it. Thank you very much, and again, once more, I'm really sorry for not being there. If you have any questions, please feel free to contact me to my email. Thank you so much.